All right, welcome back, everyone. We're going to move on to section 10.5, study 210, divergence and curl. Okay, so video here, way here. Number one, divergence. If we placed an elastic circle on this vector field here, the shape of the elastic circle stays the same. However, if we place it onto this vector field, then the elastic circle is gonna be, what do you think? Yeah, it's gonna expand, it's gonna get bigger, expand, yeah. Is that the circle expand? So when the elastic circle maintain the shape, right, we say that the divergence is zero. Expand divergence is this one. Divergence is positive. So here come a formal definition of divergence. Definition. Divergence is the expansion or contraction of a vector field. At each point. Okay, we define it to be divergent of the vector field F, right? It's the same as the divf. Well, expansion or contraction. The direction is based on the derivative, right? And the derivative has to be the partial derivative. So divergence is defined by this operation. It is the partial vector dot the vector field F. Okay, let's work it out. What is this partial vector here? If you just have the partial vector, that is the partial. It's partial with respect to x, partial with respect to y, partial with respect to z. Dot the vector field F is, a lot of people would use the P, Q, R. So, well, in the end, it's just a Px plus Qy plus RZ. Yeah. So this divergence. Next one is gonna be curl. Curl is a little bit more challenging. Okay, here come a nice definition. Well, this has to be with do with expansion and contraction, right? So in case divergence is zero, then because we have a divergence is 0 here. If divergent f is 0, we call the vector field f is call it the source free field, because it doesn't expand or contract, so that's why it's source free. Okay, here come number 2. Let's take a look at the curl before we do any example. If you put it in the field on the left side, what do you think it's gonna do here? Rotate counterclockwise. And if you place it on the vector field on the right side, then if you place the leaf here, then it just get pushed away. It doesn't rotate. Leaf does not rotate. Okay, so definition, curl of a vector field F curl of a vector field F, it is describe how a vector field F may rotate. How F rotate. So the rotation is rotating about an axis. If you draw the three-dimensional, you see that the rotation is about the z-axis. Curl F is a vector field it is a vector field, meaning that we got to define curl F using some operation so that it is a vector field. So how do you turn a vector field into another vector field? Equal curl F and this is defined by the partial derivative vector cross the vector field F. Okay, we can work it out and then you will see how this has to do with the green theorem. I told you we can see the rotation from doing curl here. I, J, K, partial X, partial Y, partial Z, PQR. Right. Okay, work out this thing here, so it's going to be a partial Y, partial Z, QR minus partial x, partial z, PR, and the last one, plus partial x, partial y, PQ. Oh, look at this thing here. This K. Right. Okay. So what do we have here? We have a RY minus QZ minus RX minus PZ plus QX minus PY. K. So this is the four. I don't know how you would remember this one. I just remember the determinant though, so I don't have to remember the formula at the end. But then the formula at the end tell us something very important. The component of curl F, that is how the vector field F rotate about an axis along the z-axis is notice that I'm going to put the green theorem here. Notice that the component of curl F along the z-axis is qx minus py for f x y. Curl F here for fxy we see that the vector field rotate about the z-axis and the rotation is described by qx minus py. This is the right hand side of the green theorem. C f dot dr is C gonna be P dx plus Q dy, and that is equal to double integral over d qx minus py dA. This one. This is a macro rotation. It's the not rotation of circulation. Along C, and this part right here is circulation at a point xy inside the region D bounded by C. Now, hopefully that you guys see the green theorem much clearer now. Huh? If f is conservative. Then, what do you guys think? Divergence of curl f is gonna be? Zero. Yeah, well, it's just zero. Right? It's just a number, zero, not a vector field though. You can quickly do the proof here. Proof. Okay. Curl f. I'll do curl first here. Curl f, right, is equal to use this thing here. Ry minus qc Rx minus pc j plus qx minus py k. And then now we use the fact that f is conservative. Well, if f is conservative, that means R is f z. Yeah? So you have a fzy minus fyz. Then this is the fzx minus fxz fyx minus fxy. Now, conservative meaning that the vector field sum this one, and then from here you know that they're the same because of the Clairaut theorem. So this would give us the 0 minus 0j plus 0k. Right. So what's this one? It's just a vector field 0, 0, and 0. So it's going to be a with the 0 vector field. And so the divergence of this 0 vector field is, of course, 0. Partial with respect to x up 0. Partial with respect to y up 0. Partial with respect to z up 0. That is 0. Okay, well, in the remaining time, we're just gonna figure out the curl and divergence. Let's do some computation here. Get a hang of it. Phi divergent f and curl F. Right. Okay. Where the vector field F is the xz, xyz minus y square. Okay. Divergent F. Everybody know how to do this thing. It's just the partial derivative here. Partial with respect to x of xz plus partial with respect to y of xyz plus partial derivative with respect to z of minus y square. And this one is z plus x z. That is it. Curl F. So curl F of this vector field you can do the determinant if you have trouble remember the formula, right? If you have the formula, using the formula may be much faster, right? So according to the formula right here, you can remember it. If not, then just use the determinant, right? I don't know, I don't remember the formula. I only remember the determinant of a 3x3 matrix, right? So I'll just do the determinant of a 3x3 matrix there. Okay. So I'll put it in here. I don't have to do the IJK. Oh, may need more room though. So okay, partial y of negative y square minus partial z of xyz. It's just the determinant here, and then minus partial x of negative y square minus partial z of xz. Then the last one is the partial x xyz minus partial y of xz. Okay, if you have question, let me know. This is the determinant of 3x3 made. I mean, this is the determinant here. Okay. And then after this one, we're gonna use the GeoGebra to sketch. And then we'll see what is going on here. Minus 0 minus x yz minus 0. Okay. Minus 2y minus xy x and yz If F is a rotating vector field, then curl F is a vector field that has arrows pointing in the direction of the normal vector, because the direction of the normal vector describe how a vector field F rotate to move from line integral. This is the very important one. Integral to surface integral. We need these operation of vector field. Line integral, everybody know, right? It's the integral C F dot dr. Right? Well, most of you can guess surface integral. It's the integral, double integral, and it's got to be double, right? Because you're gonna integrate along the surface, and this is gonna be F dot ds. Yeah. Are we gonna do the surface integral in the future section? And it's gonna be fun, right? But before that, you got to know how to parameterize the surface.